Hi everybody, hope you're all enjoying being off a little bit longer maybe than we thought. Just in case we should happen to not have school on Tuesday, I wanted to take some time out to talk about the mean value theorem. We got a start on this in class, you kind of have an idea about it, but I haven't actually done a problem, and so I thought I would take some time now and do that. So if you remember, I told you the story about my grandfather. My grandfather was leaving the airport and he was known for driving really fast. And he got pulled over by a police officer. And the police officer said, you're speeding. My grandfather came back and said, no, officer, something's gone wrong here because I left the airport 30 minutes ago. I'm 20 miles away from the airport. My speed is 40 miles per hour. And so I couldn't have been speeding. And as I told you guys in class, the police officer essentially went, well, golly gee, you must be right. Let him off, okay? Now, we've already discussed the fact that my grandfather was using the police officer's lack of understanding of the difference between the average rate of change, which is what he used, his total distance divided by his total time, and the instantaneous rate of change, how fast he was driving at a particular moment in time. And so I think most of us have enough common sense to realize he could have been driving at some constant 40 mile per hour pace for the entire time, but he also could have been driving faster and slower. And the mean value theorem speaks to this connection between the average rate of change and the instantaneous rate of change. And what the mean value theorem essentially says is the following. Just to take a simple example here, let's take a distance and time graph, okay? So let's say that when my grandfather started off, let's say that we were looking at his, where he began at some point in time and where he ended at some point in time. Let's say that he started off moving slowly and he sped up, okay? Now in notation terms, they'll usually call the starting time A, the ending time B, and again, it doesn't have to be distance and time, it can be some other relationship, but that's what I'm using in this particular case. So, starts out at a slow rate, and you can see graph gets steeper and steeper, he's speeding up, okay? What the mean value theorem says is the following. It says that if the function is continuous and differentiable on the interval, technically, it has to do a little bit with whether or not it's an open interval or a closed interval. We'll look at that a little bit more carefully when we look at the formal definition. But if the function is continuous and differentiable on the interval, then there exists some point, they call that c, it's a value of x, such that the instantaneous rate of change equals the average rate of change. Now, what does that mean? Well, the average rate of change of this function would be the slope from the starting point to the ending point. Would be the slope if he had traveled at a constant pace. He has the same beginning point, he has the same ending point, but you can do that different ways. You can speed up, you can slow down, or you can go at a constant pace. So it says that the average rate of change, which is just the slope, and by the way, we could call this, this point here would be the point B, f of B. This point here would be the point A, f of A. Basically, it just says that the slope of that tangent line, which would be f of b minus f of a, all over b minus a, has to be equal to the instantaneous rate of change at some point, which we call c, on that interval between a and b, okay? So in other words, the instantaneous rate of change, which is the slope of the tangent line, should be the same as the average rate of change somewhere in that interval, if the function's continuous and differentiable, okay? Now, it may happen multiple times, but it has to happen at least once for a function that's continuous and differentiable on the interval. And so what you're usually doing in mean value theorem problems is you're finding that value c, the place where the instantaneous rate of change, the slope along the curve, the slope of the tangent line at a particular point on the curve, is the same as the slope of the average rate of change, or is the same as the average rate of change, which of course is really just the slope of the secant line connecting the starting point and the ending point, okay? So what we can say is that the average rate of change is equal to the derivative of the function at some point c. And so what we're really trying to do is we're setting the average rate of change equal to the instantaneous rate of change, which of course we know to be the derivative. And we're figuring out where does that happen? Where's the derivative the same as the average rate of change? So it really just combines two ideas together that we already know how to deal with. We just haven't actually done any problems like that. But those are the visuals there. Now, you can get different situations. You can have a function that looks like this, and the average rate of change is still going to be the slope of that secant segment connecting the beginning and ending points. This particular example has multiple places, I didn't draw that very well, but it has multiple places where the slope of the tangent segment, that's terrible, is equal to the slope of the secant segment. You can see there's another point over here, okay? The mean value theorem is referred to as an existence theorem. It tells you that this x value occurs where the instantaneous rate of change equals the average rate of change, okay? That this c value exists somewhere on that interval. Again, it could happen in just one place, could happen in multiple places. Now, you do have to be careful. It doesn't always apply, and we're going to look at some other cases here in a minute. But for example, one place where it doesn't apply would be if the function isn't differentiable. For example, if the function has a cusp, it's possible that the average rate of change, the slope of this secant segment here, doesn't match up with any slope on the graph because you're jumping from one kind of slope to another kind of slope, and it's essentially possible you're going to skip over one of those possible slopes that might equal the average rate of change, the slope of that secant segment. So you're going to see different kinds of things with these problems. That's kind of an overview of what this looks like visually. And next I'm going to take a look at the formal definition.
All right, this is the investigation that Foerster had us take a look at. You can see here he gives us kind of a basic case here. Notice the function is smooth, which means it's differentiable. No cusps. It's also continuous on the interval between the two different points here. In this particular case, between the points at 3 and 7. So you can see, if you draw the secant segment in here, you can see there's a place maybe approximately right here where the tangent line has the same slope as the secant segment, and that's where your point C would be. So it's some value, looks like it's maybe a little bit more than 5, maybe 5.2, 5.3, something kind of like that. Okay, so that's the basic idea. The function's continuous and differentiable on the interval. Okay, notice this example, the function is still continuous and differentiable on the interval, and notice you're not guaranteed just one value of c. There could be multiple values of c. You can see here there are two places where the slope of the tangent line, the instantaneous rate of change, is equal to the slope of the secant line, which is the average rate of change. So it's not just one point, you could have multiple points. Okay? Notice here the function has a cusp, and as a result, because we jump from one kind of a slope to another kind of a slope, it doesn't pass through every single slope, moving from the slope here to the slope over here, it's possible that there's no place where the instantaneous rate of change, the tangent line slope, is the same as the secant line slope. So this is a case, because this has a cusp and is not differentiable, the mean value theorem doesn't apply. Okay? Again, that doesn't mean that you can't have a slope that's the same as the average rate of change. It just means that the mean value theorem doesn't guarantee any possible point. Okay? Now notice here, there's a cusp, but it's at the end of the interval. The function is completely differentiable in between the 2 points. We say it's differentiable on the open interval, basically not including those 2 points. And notice here, it's a little hard to draw that, but you'll notice that there is in fact a tangent line that has the same slope as the secant segment. So it's not just that there's a cusp anywhere. If there's a cusp at the endpoints, that's okay. Just can't be a cusp somewhere in between the 2 endpoints. All right, we'll pick up on the back side here. We're going to look at what happens if functions aren't continuous. We're going to look both if it's discontinuous in the middle of the interval or if it's just discontinuous somewhere in the interval. So you'll notice here the average rate of change would be between that beginning point and that ending point, and you'll notice there is no secant line, there is no tangent line that has the same slope on this interval as that secant line. So you can see there that if the function is discontinuous, even if it's discontinuous just at one of the endpoints, that's enough to make the mean value theorem fail. Okay? Now, is it possible to have it work? Yeah, it is. It is possible to have it work. For example, you can see here, if you find the slope between the essentially f of a and f of b, we're looking between 5 and 9 right here. In this particular case, it does look like there's a point down here where the tangent line has the same slope as the secant line. So we've seen a case where we have a discontinuity at the end of the interval that doesn't work. We have a case where it does work. Okay. However, if it's not continuous over the entire interval, including the endpoints, we're not guaranteed that the mean value theorem will work. Okay. Here's another example. Now, this one you'll notice still has a discontinuity, but it's continuous over the closed interval. And so the mean value theorem will apply here. So the mean value theorem applies if it's continuous over the closed interval, so that includes the endpoints. Doesn't mean that if it's not continuous including the endpoints that it can't work. It's just not guaranteed to work unless you have that particular case. All right, here's the actual wording for the mean value theorem. The conclusion is the function has to be differentiable and continuous on the interval between a and b. Notice that it just has to be differentiable on the open interval. So you can have that cusp at one of the endpoints, that's totally okay. You just can't have a cusp somewhere in between the interval. And it's got to be continuous for the entire interval, and that includes the endpoints if you want to guarantee that the mean value theorem is going to work. And then you'll see here that the theorem guarantees that there exists some number, a value of x that we call c, in the open interval, so that's between points a and b, not including points a and b, such that f prime of c, the derivative at that point, is the same thing as f of b minus f of a all over b minus a, the average rate of change. That's the wording of the mean value theorem. Now we're going to see two examples of how it works.